Hello, so we're going to take this matrix F, which is a 3 by 3 matrix, and we're going to use the Cayley-Hamilton theorem to find f to the fifth, and if possible to find the inverse of f. So to use the Cayley-Hamilton theorem, we need to get the characteristic polynomial of this matrix. Now you can do that by expanding out a determinant. That's one way of doing it. So you take the determinant of 2 minus lambda, 1 minus lambda, 1 minus lambda, and the rest of the matrix, expand it all out. I might do this one slightly differently. That's the way we've been normally doing it in class. I might do this one slightly differently. Just look carefully at the matrix firstly, and you'll see that if you add the second and third rows, you get the first row. So that means the rows of this matrix are linearly dependent, which means the matrix has no inverse, which means its determinant is 0, and as the determinant's the product of the eigenvalues, then one of the eigenvalues at least must be 0. So I'm going to do this by writing down the eigenvalues. Well, one of them's obviously now 0 because the determinant of the matrix is 0. If I stare at it for a minute, do you see also that if I subtract 1 from the main diagonal, I'm going to get 2 rows here, 1, 0, 0, 1, 0, 0. So, and they'll be dependent, so lambda equals 1 is another obvious eigenvalue. And then from the trace, the other one must be 3 from the trace. So once I know the eigenvalues, they're the roots of the characteristic polynomial. So I can write down the characteristic polynomial without doing the determinant expansion. It has to look like, it's got to have a root lambda, lambda minus 1 and lambda minus 3. So there's the characteristic polynomial fairly easily, in the case where you can easily guess the eigenvalues. Now I'm going to expand this out, so this is lambda cubed minus 4 lambda squared plus 3 lambda. So by the Cayley-Hamilton theorem, this remarkable theorem that says that the characteristic polynomial, if you replace the variable with the matrix and any constants with an identity, then it satisfies its own equation, which is quite a remarkable fact. So by the Cayley-Hamilton theorem, we can say that f cubed minus 4f squared plus 3f is the 0 matrix. And that means I can write f cubed then is 4f squared minus 3f. Now by the way, let me come to the inverse thing firstly. It says find if possible the inverse. Well, we saw that the determinant of f was 0, so f has no inverse. F has no inverse. We can see that also in the constant term being 0 of the characteristic polynomial. So now I want to get myself up to f to the fifth. Well, firstly we go to f to the fourth, so you multiply by f. So I get f to the fourth is 4f cubed minus 3f squared. And the idea now is to sort of bootstrap and replace the f cubed back in terms of smaller powers of f, so that's 4f squared minus 3f squared, and that gives me 16 minus 3, which is 13f squared minus 12f. So you see what I'm doing, I've written f to the fourth now as a combination of f and f squared. So to get to f to the fifth, do exactly the same thing, that's 13f cubed minus 12f squared. Replace the f cubed, as we did before, with 4f squared minus 3f minus 12f squared. So now we just take out the brackets and simplify, so 13 times 4 minus 12 gives me 40f squared minus 39f. And there is the value of the fifth power, expressed only in terms of f and f squared.